Hi, this is Grant Dower, and this is 2212 Lab 5 Faraday's Law. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet and tube interaction computationally, and compare the computational predictions with the observed data. Some fundamentals are Faraday's Law, Newton's second and third laws, the Biot-Savart Law, Ohm's Law, magnetic force on a loop, and magnetic flux. Some models and assumptions. The magnet was used as a model for the magnetic dipole, and the roll of aluminum foil modeled the tube through which the magnet fell. Assumptions: air resistance is negligible on the falling magnet, and the magnetic force and the force of gravity are only forces acting on the falling magnet. Experiment details: this system is a tube and magnet, surroundings, everything else. Procedures: use a magnetometer to mark north pole of the magnet, drop the magnet through the tube and record fall time as shown through this model here, and repeat this drop 5 times. Data: 2 blanks, 0.3 meters, width 0.005, 0.02 for the inner radius, 0.03 for the tube radius. The mass of the magnet was 0.025 kilograms. Average fall time was 1.21 seconds as shown here, and the mu value from lab 3 is 2.285. Why can't a ferrous tube such as a steel pipe be used? Steel contains iron, which has magnetic properties. This can create magnetic fields that affect the data. What happens to the magnet? How does this compare to a magnet falling in free space with no tube? The magnet falls through the tube slower than it would in free space due to the upward magnetic force on it caused by the induced current in the aluminum tube. So here's the glow script code. So just up here is initializing physical constants. This creates the graph initialization, the 2 aluminum foil. Here's some initial conditions, calculated magnetic flux, defining the dipole. This is simulated in the loop, motion prediction visualization, the gravitational force on the magnet calculations, the second part of the calculations for the gravitational force. And this is the computational model results. So this first graph is using my mu value from lab 3, which had the pretty far off time to fall, 0.406 seconds. So then I experimented and found a mu value of 4.305 that matched my value for how long on average the magnet took to fall. This shows the magnet falling through the tube. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate a current flowing in opposite directions. Which color corresponds to clockwise current as viewed from above, and which counterclockwise? How do you know? So the red ring corresponds to counterclockwise and blue responds to clockwise. I know it's through Lenz's law. What happens to the dynamics of the system when you flip the magnet around? Nothing. The magnet still follows slowly compared to if it was in free space falling. The current direction is flipped though. How does the total time in tube of your real world system compare to that of your computational system? How might the computational system be made more accurate? Both are pretty close to each other when using a second mu value. This would be more accurate if the tube is split up into more rings, or by finding mu in a more accurate manner. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? At first, the gravitational and magnetic forces are unbalanced, and then when the graph levels out, constant velocity, the forces are balanced, and then when the magnet falls out of the tube, they're unbalanced again. There's no model discrepancies. Some possible sources of error are human error in measuring the drop time and an incorrect mu value from lab 3. What if the resistivity of the conductor were reduced as close to possible to 0? How would the dynamics of the falling magnet change? If the resistivity dropped to 0, then there'd be a larger induced current because same induced EMF over low resistance, which would increase the magnetic force upward on the magnet. And if it's large enough, it would counteract the force of gravity, which would cause, in theory, to float. The magnet would float. What if holes or slots are cut into the tube? How would this affect the ring currents in your model? Holes or slots might disrupt the induced currents in the tube, which could lead to weaker magnetic forces, causing the magnet to drop faster. Conclusion: this lab helped me to develop a more solid understanding of Faraday's law and how it can be used in real life situations. better understand induced EMF and current caused by changing magnetic flux, and learn how to model fundamental physics ideas with everyday